Hello, friend. My name is Derek Harder, and in this video, we're going to take a closer look at how the recurrent layers in a recurrent neural network actually work. So hopefully we'll give you some details about the actual inner workings of how they're implemented, and we'll also, of course, look at the different implementations of recurrent layers that are available in Keras and how you might use them in your model. All right, so let's go ahead and get started. Okay, so a major characteristic of all the neural networks that you've seen so far is that they don't have any memory. Okay, so each input to, for example, think of a dense layer, is the various inputs, the various features coming in are all processed simultaneously in parallel and are pretty much kind of independent of one another. At least there's no particular state. So in a time series, all the things coming in really are related to each other. There's a causal relationship. Okay. So for example, in the previous example that we did, we flattened 5 days of data into a single large vector to bring into like our first model that was a simple feed forward network. Right. So biological systems, for example, humans, that you use memory when you're doing things, right? So think about when you're reading, you process words sequentially, usually keeping a memory of what came before. Okay, and kind of as a thing thinking about the future here, so it's not uncommon to process words sequentially, but you'll skip around. So you might change your focus of attention and go back. You might scan some things, then find something that you more closely watch. So usually when you're focusing in on something, though, you'll read the words in sequence, and you'll kind of be building up a memory of what you've read before to get a complete understanding of a sentence or paragraph that you're trying to work through, right? So a recurrent neural network, a recurrent layer in a recurrent neural network adopts that same process. So it's going to process the inputs of a time series sequentially by iterating through the sequence elements. It's going to maintain a state. So looking over here, basically the input, think of this as the input for time 1, time 2, time 3, time n for a sequence. It's going to process the time 1 input, do its processing, and it'll get the output for time 1. And it's going to remember something, so it'll feed that back in. So when it's processing the input for time 2, it's going to be combining time 2 input with what it's remembered so far to get the output for time 2, and so on, right? So it's conceptually, you can think of that as it's processing the elements sequentially that it gets as a time series, as a sequence that has some causal relationship. So a recurrent layer in a recurrent neural network adopts that same principle. So it's going to process sequences by conceptually iterating through them from the one at time 1, time 2, time 3. And each time it does it, it's going to be performing an operation, and it'll feed back in the result of that operation that it outputs for each input. So each time it's processing the next item in the sequence, it's processing both the item and its memory. It's recurrence that comes back in the state. So we call that the state of the recurrent neural network. So when you feed in the next batch, when you feed in the next sample, you do reset that state and start over, right? So this sequential iteration is happening for one sequence, time 1, time 2, time 3, time n. So again, for our previous example, we had our sequence length with 120. We had 120 samples, 5 days, 24 hours of them. That came out to 120 samples. So each time a sequence comes in, there'll be 120 iterations. Okay? So you can think of this as some Python pseudocode. So it's as simple as this. So what happens for a single input sequence that's a time series is we iterate over each input in the time series, and we perform some function. So, these are tensor operations. So we'll get more details in the next slide here to get the output, and that updates the state, right? But notice that that tensor operation is a function of the current input that's coming in and the previous state that we have, right? So when we generate the output for time t, we're also going to keep track of that state and feed that back in. All right. So to be more specific, what those operations are is, you're familiar with that. It's basically performing a tensor operation. So it will keep a set of weights, that it will do a dot product of the input for time t with the weights. It has two sets of weights in the case of most recurrent layers. So, call those W and U. So the other weights are multiplied by whatever the current state is at time t. There'll be some biases. So this is just a simple tensor operation. We have two dot products in this case. Add in the biases, and we'll feed that through an activation function. Okay, so that's specifically what's happening. And remember, so what you learn is, these W and U will have to have the same shape, but these can change the shape. So the input, so we might be inputting 14 features here, and because of the shape of W and U, we will output that's the same parameter like for a dense layer. So we might be outputting a different set of 64 features as the result of this activation. And that happens because of the weight, or the shape of the weights that we use in the dot product here. So to make this process completely unambiguous, let's look at some actual kind of code of that pseudocode, the actual working Python code of that pseudocode, right? So here, let's say that we have so in this small example, let's say that the number of time steps for a single sample is 100, and has 32 input features. So, remember for our previous example, the number of time steps was 120, and there were 14 weather measurements that came in. So each time step, there was 14 measurements of the weather that happened here, right? So that's our input. And again, the result of doing our tensor operations is the output at each time step is going to be 64 output features due to the tensor transformations that we do, right? So, we need a, so we'll just make up some random inputs, right? So this is really just pseudocode, an example. And the state, so the result of doing the tensor operations is there will be 64 outputs at every time step, okay? So, look at our weights here. So if we want to transform from input to output features, our weights, this will be similar to what we had to do for a dense layer, right? So it'll have in this case, a 64 by 32 shaped W and U matrix, right? So the result of multiplying one of these times one of our inputs, just a single one of the inputs, is we will end up with 64 outputs. We'll come in with 32, we'll go out with 64, right? So we'll talk about this in a moment, but the result of the output from iterating over a single sample, and I should have mentioned that in this case here, like our inputs, we only have one sample, so we're don't worry about a batch now. But you do the same thing. If I have 32 batches, I would just have to do the stuff down here below 32 times, right? But we just have one batch coming in that has 100 time steps with 32 input features. Okay. So then our pseudocode looks like we showed before. And in this case, I started saying that a recurrent layer can output just the final output, but sometimes we need it to output all of them. So, we'll iterate through this loop 100 times, if we need to, we can capture all 100 of the outputs that we do and return now, which is what we're doing in this example here. So then again, this loop, hopefully you've understood everything there. This loop is doing what we said. We're just doing our tensor products, so dot products of the input times the W, an additional U matrix times the previous state that we have. So initially the state just starts off as 0, right? Or it's going to be 64 zeros because the output result of this is 64 for the example that we're showing. We add in the biases. And this could be any activation function. So historically, when recurrent neural networks were first made, they used tan-H output function, but this could be RELU or sigmoid or some other activation function. And then if we need to, we keep a history of the successful outputs. And then here's the update. So the state that you remember, you just remember the output that you just generated. And that comes back into the next iteration. So the result of this is that we get a single sample of 100 of a time series that's 100 steps long with 32 inputs, and then the result for the final output sequence is that we have 100 of those, right? So we had 100 times for this loop. Each time the output of the loop had 64 outputs, right? So the one at index 0 was the first output that we calculated, and the one at output 1 and so on. The one at output 99 was the last output from sequentially going through our time series here. So in summary, an RNN, you can think of it as a for loop that reuses quantities computed during the previous iteration of the loop, right? So we could draw this as kind of a flow graph. So basically what's happening, so for input at the previous time step, it will generate an output using tensor operations, right, that you're familiar with. And that output, though, is fed back in for the next iteration, right? So we'll have the state and the input at time t, and we perform those tensor operations to calculate the output t, right? And that keeps happening. Okay? So another thing that I want to mention about this figure here is, so like in reality, for performance reasons, this kind of unrolling might actually be done. So instead of having a loop that you iterate over, based on the size of the time series, if it's not too big, you might actually take the time to unroll this. So you have a sequence of these operations instead of having a loop. So you can turn it back into just a big matrix multiplication. Okay? And also you have to conceptually or in actuality do this kind of unrolling to do the gradient descent, right? So to calculate the gradients, usually what you do for a recurrent neural network is you unroll it like this so that you can calculate the gradients with respect to time t plus 1 and then time t minus 1 and so on. So this unrolling is how you can think of when you come to the point where you need to do the backward propagation and calculate gradients. Something like that is happening behind the scenes. Okay, so as we hinted at before, all recurrent layers in Keras, like the LSTM and the GRU that we talked about, can be run in two different modes. So they can return the full sequence of successive outputs for each time step. So that's what we did in our previous, more worked out pseudocode example. Right. So in that case, it's if you add back in batches. So usually this is going to be done in batches. It returns back, like in previously, it returned back how many batches we had, and we had 100 time steps, and we were outputting 64 features from this layer. Right? Or you can return just the last output as a result of doing that from the layer. So in that case, you get around 2 tensor of just the however many batches you had, the number of output features, like 64. Right? So these are controlled by the return sequences constructor. Okay? So real quickly, what that looks like as an example, if you only want to return the last output, we say return sequences is false. So in this case, we turn to like our Jenna weather example. So we have time series that have 120 time steps in the series, and there's 14 features coming into the first input layer, right? And we're going to create something that will, a simple recurrent layer that has 16 outputs from it. And it's not going to return the full sequence of outputs, right? So the output shape should be, what do you predict? Should be however many samples that we had. So we don't have any, we're not actually doing anything, but it just returns the last 16 outputs from iterating over the 120 times. Or if you say return sequences is true, this would be like our example. You'll get a 3-dimensional tensor of the number of batches that you have, the 120 separate steps, and then the 16 features that will be computed in this layer. So, and you can stack layers. So, you're familiar with this kind of concept for dense layers or convolutional layers. So we could take our inputs with 14 features and run that through a recurrent layer that outputs 16. That comes into another recurrent layer that outputs 32, and then another layer that outputs 16 in this case. So you get the expected, and we're always returning the sequence. Well, we're returning the sequences for the first two, and the last one only returns the final output, which is kind of something that you might see done in some real recurrent neural networks here. Okay, so in practice, for a real problem, you probably shouldn't use just the simple RNN layer. There is a simple RNN layer for Keras. So we'll look at a bit here, but the simple RNN has a major issue. It's that vanishing gradient issue that we talked about. So again, think about, I mentioned the idea of unrolling. So, if I have a sequence of 120, that's conceptually as if I have 120 layers that you'd have to pass the gradients through. So they will rapidly run into the vanishing gradients problem if you're using simple RNNs on any kind of time series that has more than a few items in the sequence that you're working with. So yeah, each loop acts as a layer. So for a large number of them, you're going to get the gradients will diminish, vanishing gradients. So basically, the reason why you have to use LSTM and GRU is they essentially have the residual connections, the skip connections that we saw in our previous unit on convolution, big deep networks, right? So we need those sorts of residual connections in these kinds of recurrent layers in order to mitigate these vanishing gradients. So that's really what the LSTM and the GRU is a later version, it's a little bit simplified version of the LSTM. When you read about the LSTM, it seems a bit unnecessarily complex. It's probably not important that you understand kind of the nitty-gritty details, but yeah, the LSTM really is a variant of the RNN, but it adds in this idea of a carry. So the carry is really kind of doing the functions of the residual skip connections. Okay, so essentially it saves that information for later, thus preventing the older signals from gradually vanishing during the process. So these are kind of similar to residual connections. So the implementations in GRU are a little bit more direct of the sort of residual connection that we've talked about. So just real quickly, a little bit about some of the details. So what kind of happened, so this is that carry back, right? So it directly goes through, or at least in this picture, it directly goes through, but we feed in the state. Now, the states are going through these transformations, but then basically the operation that's happening is a function now of the input, the state, and the carry. Right, but then the carry kind of more directly goes through, and it can act as a kind of a skip connection. Right? So it's actually technically more complicated than that. In particular, there is a computation that's going on for these carries and the output and the input, and the carries that are coming through. So I don't really want to describe all those, but yeah, in short, these operations are actually determined by the contents of the weights parameterizing them. So there is kind of an update that's happening on these. And the weights are learned in an end-to-end fashion. But I will just say that it's different from the tensor operations that have here. So these can act as a kind of residual connection for LSTM networks. And again, GRUs are doing something similar. They're actually a little bit they're doing the same thing, but they're a little bit simpler architecture. All right, that's basically it for this video. So just kind of a quick summary of the stuff that we went over here. So recurrent neural networks, or the recurrent layers basically in a recurrent neural network, they process their sequences by iterating through them. So you can think of them as iterating from time 0, 1, 2, 3 of the sequence that they're currently processing, right? And they maintain a state. So it's actually simple, because the state is really just the output from doing the tensor operations. But that state is fed back into the recurrent neural network for the next item in the sequence that's processed. Okay? So all recurrent layers in Keras can be run in 2 different modes. So they can return the full sequence history, or they can return just the last output. So we'll have more about that later on. We should kind of keep that in mind. In practice, you shouldn't use the simple the simple RNN layer for a real problem because it suffers from vanishing gradients. So the LSTM and the GRU basically add in kind of a carry flow, which acts similar to residual connections. Okay? Like I said, that's it. That's the basic ideas of what happens in the implementation of a recurrent layer in a recurrent neural network. Hope that was useful for you. And next time we're going to get into actually using some more details, advanced uses of a recurrent neural layer. So I hope you'll come back and stick with me for the next video.